Mackenzie Mountains. And I'd also like to thank you for staying late today to watch what I have to say. So here is a picture of graduate student David Heath taking out a seismometer in the Mackenzie Mountains. And I will show you where they are in a minute. Oh, here we are. I'd like to thank my co-authors, the graduate students that have worked in the field and worked on the research, the National Science Foundation, and also the First Nations peoples on whose lands the seismometers were deployed on. And here is graduate student Derek Witt on the left and collaborator Joel Cubley of UConn University on the right, looking at a seismometer. So the Mackenzie Mountains are located in Northwest Canada, as shown by this shape here. It's a very remote part of Canada. It consists of the Yukon Territory to the left and Northwest Territories to the right. This is what we thought of the Mackenzie Mountains before our project. The leftmost plot here shows lithospheric thickness inferred by the method of Richards 2020 from a global surface wave model. What we expected to find was an area of thin and hot lithosphere to the west, cold lithosphere shown by the blue to the east, roughly divided by the deformation front, which is shown by the line with the triangles on it. And as an example, I give the contour depth of where the lithospheric thickness is about 170 kilometers depth by the red dashed line here. And you can see they correspond pretty well. So this is what we thought that we would see. To the right, I show the various accreted terrains of the area. So to the east, we have a craton. This hasn't been deformed in the last billion years or so. And then moving to the west, we see initially the Mackenzie Mountains, which has a paracratonic affinity. And then as you move further west, I see a series of exotic terrains. And these exotic terrains have been accreted on to the Canadian margin over the last 150 million years in a series of transpressional events. What's notable also is there's a series of faults, the Teslin-Thibert. Can you all see my mouse? Can you see my mouse move?
Yes.
Yeah, okay. So the Teslin-Thibert is this one here. The Tintina fault is this fault here. And the Denali fault is this fault here. The first fault that was active was about the Teslin-Thibert fault, which was active about 60 million years ago. Then the Tintina fault became active about 40 to 50 million years ago. And then the Denali fault became active about 20 million years ago. The Tintina fault and the Denali faults both have 400 kilometers of right lateral slip on them. So these are huge faults. What we knew tectonically before our project was that the Yakutat block, which is an oceanic plateau sitting on the Pacific plate, is subducting under Alaska. So here's Alaska, here's the Yakutat plate subducting under Alaska. It's creating a lot of deformation as this plateau, which doesn't want to subduct, is sort of squeezing the land. And it's creating the Wrangell-St. Elias range, which has some of the highest rates of uplift in the world. What seems to be happening is strain is being rotated into a northeast-southwest orientation and forming the Mackenzie Mountains, where there's 1 to 5 millimeters of year of deformation. And this is interesting because the Mackenzie Mountains are an arcuate-shaped mountain range that actually stick out further than the limits of the Cordilleran deformation front further south in Canada. So they seem to be unusual in the fact that they stick out so much. We can look at GPS instruments, and what we see is under the Yakutat block and to the north of the Yakutat block, most deformation is in the direction of the Yakutat North America convergence direction. So here to the northwest. But there seems to be a rotation as you move east, and the circles here show a northeast directed deformation. These arrows are with respect to stable North America, which is somewhere over here. So what this means is the area is converging in a relatively uniform manner as the plate motion drops from whatever these arrows show to 0 somewhere out further east. So what we think is happening is the Yakutat plate is moving under North America, and there's deformation in the direction of the Yakutat plate to the west, but then there's a strain knot, and somehow that causes a rotation of the strain to the east, causing 5 to 10 millimeters a year of deformation, and the Mackenzies are out here. We can look at seismicity in the area. So to the left here, I show the Mackenzie Mountains, and you can see it's a fairly high area of fairly high seismicity. And then as I go inboard from the Mackenzie Mountains towards the plate margin, there's an area of fairly low seismicity until I get to the Denali Fault, where there's a lot of seismicity. So what we think is happening is this area here between the Mackenzie Mountains and the Denali Fault is actually not uplifting or doing anything, really. If I look to the right figure at earthquake focal mechanisms, we can see in the Mackenzie Mountains that we have mostly thrust events. So this suggests that the Mackenzie Mountains are currently actively uplifting, yet they are 700 kilometers from a plate margin. So a question arises, how do you get active uplift 700 kilometers from a plate margin, and then you have an area closer to the plate margin where you have no active uplift? So I'm going to show a transect from southwest to northeast. And here is a model that was put forward by Mazzotti and Hinman in 2002. So you'll recall that I suggested that the lithosphere to the west is weak and thin. They modeled that. Here's a rheologic profile of the Cordillera. And then they put a strong and cold lithosphere to the east. Here they modeled it as a covered craton. Oops. And then what they did is they created a two-dimensional model where they imposed 5 millimeters of year of strain on the crust. They put a weak foreland belt at the margin between the Cordilleran and the covered craton rheologies. What they find here is in figure D. And what they found is that you get a lot of deformation right at the source, which corresponds to the Wrangell-St. Elias range. And then you get a undeformed region of upper and middle crust that slides on a mobile lower crustal layer and is uplifting in the Mackenzie Mountains. So this is one model for the cause of the Mackenzie Mountains going up today. And it depends on the Yakutat collision. Another model that has been put forward has been by Finsel et al. They have modeled boundary forces, so plate boundary forces and gravitational potential energy, and they've matched that to GPS deformation. The responding, what they found is that they need tractions at the base of the plate that will help match the boundary forces and gravitational potential energy to the GPS. So these arrows here show the tractions they predict at the base of the plate. Now the Mackenzie Mountains are up here on the rightmost part of their model. So this model is not very accurate at this region here, but what they've found is an area of convergence. So there's tractions to the northeast on the west side of the Mackenzies and tractions to the southwest on the east side of the Mackenzies, which would create a scenario where you would have uplift. So we want to evaluate those two models and potentially other models for the formation of the Mackenzie Mountains. And I'd note that a lot of these figures show Alaska predominantly, even though we're interested in the Mackenzie Mountains. And that's because Alaska has been well instrumented in the past, whereas the Mackenzie Mountains has been an area that's had almost zero geophysical exploration. So it's almost been an afterthought. To add some complexity to the scenario, looking at apatites and zircons, Enkelman et al. Found 3 phases of uplift of the Mackenzie Mountains. They found one at between 180 million years, one phase at between 40 and 65 million years, and then a third phase at 20 to 35 million years. What's interesting is that they don't find uplift corresponding to today's uplift and deformation. So this means either that this transect that they did, which actually didn't sample very many locations, just didn't get a location where there's coherent uplift currently, or that the current uplift hasn't created enough deformation to cause cooling yet. So that would imply that the current uplift phase has just started. So to look at what's happening, we put in a bunch of seismometers. And to give you an idea of what was known of the area in the past, here on the left, I've shown you the seismometers, the temporary and permanent arrays that were in 2015 and before. And you can see there's a fair amount, but keep in mind that we're talking from here to here is 800 kilometers. So this is actually fairly sparsely instrumented. The array down here is called the Canoe Array, and that was in from, I think, 2004 to 2006, and then it got pulled out. So what we did is we put a line of seismometers as shown by the red triangles across the Mackenzie Mountains. So this was an 1,000-kilometer long array of 40 seismometers. And that in conjunction with the transportable array, which was placed in here, and some other seismometers that were placed in northern British Columbia and northern Alberta provided the background for our data analysis. And I'd like to emphasize here are the Mackenzie Mountains. This border here shows the border between the Northwest Territories on the right and the Yukon Territory on the left. And as you can see, there's almost no seismometers in the Northwest Territories. So we called this the MMEP, the Mackenzie Mountain Erscope Project Array. To give a feel for the logistics involved, the red line shows a rough transect along our array. And from Carcross to McMillan Pass, which is right at the Yukon Northwest Territories border, most of the array was spanned by a four-wheel drive road. Here I show a field vehicle with the Mackenzie Mountains in the background. This is actually a fairly good part of the road. The road was actually only maintained once a year, and it's only accessible in the summer. So right now, for instance, it's in winter conditions and it's not going to be accessible until June again. And then for the Northwest Territories part of the array, so the Northwest Territories is all this colored area in, we had no roads. And so we had to access our sites by float plane. So we landed in a lake. We'd often wade from the plane to the lake and bring our seismometers in. And here are two graduate students, David Heath and Connor Droff, putting in a seismic station. All right, so I first would like to show you the preliminary results of some ambient noise imaging. This is actually a work in progress, so it might change a little bit. But what we've found so far is at 10 seconds and 20 seconds Rayleigh wave phase velocities, we see a low velocity region at the Mackenzie Mountains, but surrounded by high velocity regions to either side of the Mackenzie Mountains. And we see also high velocity features associated with the Tintina fault. If I go to 20 seconds phase velocity, I see a slightly more coherent image, low velocities under the Mackenzies, and then higher velocities to the south and to the west of the Mackenzies. So what this is suggesting is that crustal structure, since 10 or 20 second Rayleigh wave phase velocities are really most sensitive to crustal structure, shows these large scale variations in velocity that don't correspond to what we know about the accreted terrains. So since crustal velocity variations are either due to composition or fluids, right now we think that there may be substantial fluids or even magma below the Mackenzie Mountains. Here I show the 30-second and 40-second Rayleigh wave phase velocities. So this is sensitive now more to the uppermost mantle. And what we can see is low velocities bleeding off to the west here. And again, high velocities to the south and the north of the low velocity Mackenzie Mountains. We can invert for S-wave velocity, and I'd emphasize this as preliminary work. And what we find then is low velocities under the Mackenzie Mountains, and then high velocities just to the west of the Mackenzie Mountains. And that seems to be associated with the Tintina fault. And here I see at 40 kilometers depth, there's an area of larger low velocities and also high velocities to the west of the Mackenzies. So what this is telling us is our velocity structure is very different from what we thought it would be. So we initially thought that everything to the west of the Cordilleran deformation front, shown by the line with the triangles, would be low velocity and weak lithosphere. But what we're finding is there's actually complex structure. So next, I want to look at receiver functions. So receiver functions map the depth of P to S conversions. And I'm going to show you 3 lines, one across the transportable array, one across the MMEP, and one across the Canoe Array. And in particular, I want to draw your attention to the Mackenzie Mountain Erscope project array and look under the Mackenzie Mountains themselves. And what we see is an area of thin crust going to thicker crust and then back to thin crust again. This is the Tintina fault here, and this is a Cordilleran deformation front. So this is corresponding to the triangle line in the leftmost figure. So we can plot the crustal thickness as these green circles on the map. And what we see is areas of greater thickness right in the western part of the Mackenzie Mountains. We can map this into 2D velocity or 2D variations in crustal thickness. And what we seem to see is an area of increased crustal thickness on the edge of the Mackenzie Mountains and also up in the Richardson Mountains up here. We don't have any data for the southern extent of the Mackenzie Mountains, so we don't know if that's been thickened or not. But we can say that the area of thicker crust here, the gray area shows areas where the crust is 36 kilometers or thicker, seems to correspond to the area of heightened seismicity. And here you have the focal mechanisms, again, showing mostly thrust faults around the Mackenzies. So what we think is happening is that whatever is causing the deformation is creating thrust stacking. And again, I'd note that there's very little deformation to the west of the Mackenzies until I get to the Wrangell-St. Elias range and the Denali fault. Pascal Audet has also looked at the lithospheric thickness. So this blue line shows the lithospheric thickness, or what we presume is the lithosphere-sinosphere boundary. And what he sees is basically that it's 50 kilometers in depth, or 10 kilometers basically below the Moho. And this is a transect through the Canoe Array, A to A prime. So it's a bit to the south of the Mackenzie Mountains. So what we think right now is the lithosphere is quite thin in this area. We can look at earthquake-based surface wave tomography. So this is S-wave velocities derived from surface wave phase velocities and group velocities. And what we see is a low velocity. Here it's slightly oriented to the south of the crustal low velocity anomaly. But again, a low velocity under the Mackenzie Mountains, and then low velocity to the west of the Mackenzie Mountains, and then a high velocity feature basically south of the Mackenzie Mountains. Again, now this is in the lithospheric mantle, maybe even in the asinosphere. And what we're seeing is a complex lithosphere with dramatic velocity variations, which probably correspond to temperature variations. Here I show 70 and 80 kilometers depth. We can see the anomaly to the west. The low velocity anomaly is growing in size. Here, the 80 kilometer figure on the right, again, the low velocity feature is growing in size, but I also have a fairly high velocity feature just to the southeast of it. And here at 90 kilometers depth and 100 kilometers depth, we can see we are probably in the asthenosphere here. So what we're seeing is probably some sort of upwelling. There could even be some magma associated with this. And then high velocities just to basically surrounding this. So we think that the lithosphere is much more complex than the simple sort of thick to thin transition that I originally told you about. So we've done body wave tomography, and the colored circles show the mean station travel time residual for P waves on the left and S waves on the right. If I look at the P wave figure on the right or on the left, what we see is delays or low velocities, basically starting at the Cordilleran deformation front, but also corresponding to east of the deformation front in the south. And I'd also note that there's the lowest velocities under the Mackenzie Mountains right here. So that allows us to do body wave tomography. And at 100 kilometers depth, we see this low velocity feature under the Mackenzie Mountains. And this is also shown, seismicity is shown as with the gray circles. And volcanoes are shown with the red triangles. So we see an area of low velocity extending to the west and a little bit to the south, and an area of high velocity just to the south of the area of low velocity. We see this at 150 kilometers depth and 200 kilometers depth, and even at 300 kilometers depth. So next, I want to show you a transect. I want to show you B to B prime and C to C prime, which follows the Mackenzie Mountain Array. So I want to focus first on B to B prime. This transects mostly low velocity features, and then it goes through this high velocity feature up here. B to B prime, it sees a little bit of a high velocity feature, F, which is shown here in the 100 kilometer depth figure on the bottom left here. And then it goes through D and A. And so what we're seeing is A seems to be cratonic affiliated. And this has been proposed to be a basically new craton or a fragment of the craton called the Mackenzie craton. D seems to be the low velocities, potentially affiliated with the Mackenzie Mountain low velocities. And F is interesting because it's a fragment of something, because it's actually only 100 kilometers wide. If I take the transect from C to C prime, so if I go to the leftmost figure here, C to C prime follows the Mackenzie Mountain Array, what I see is low velocities, then high velocity is shown by E, and then low velocities again, and then moderately high velocities. So we see E here looking at the 100 kilometer depth map to the lower left. What we see is E is high velocity, and then low velocity, and then moderately high velocities again. So this really shows us that the situation is much more complex than a thin and hot lithosphere to the left and a cold lithosphere to the right. Now, we can't really say too much about the depth extent of the anomalies. Here is a synthetic velocity variations put in from U to U prime. So U to U prime here shown on the right goes across the Mackenzie Mountain array. What we see is that if I put in the velocity variations that are shown in the upper leftmost figure, I get back the velocity variations shown in the bottom leftmost figure. And so what we see is there's some significant streaking. So it's difficult to determine the depth extent of the velocity anomalies. So what we found so far is that body and surface wave tomography has shown scattered high and low velocity features to the west of the deformation front, which was unexpected. Low velocities in the center of the Mackenzie Mountains and often off towards the west. And also, if I displace C 400 kilometers and I account for the Cenozoic offset of the Tintina fault, C corresponds with A and E corresponds with B. So we seem to see this lithospheric fragments that have formed that have been sheared off by the Tintina fault. And here I show the current velocity variations to the left, and then the velocity variations where we've moved the velocities to the west of the Tintina back by 430 kilometers. And you can see that D corresponds to this velocity variation here. So here to the left, here's D, and here's, oops, sorry. See if I can go back. Oh dear. Sorry about that. So D corresponds to this high velocity variation and F corresponds to this high velocity variation. So we seem to be seeing lithospheric scale deformation going on here. It's possible that deformation is focused by the low velocities. Whether or not the low velocities in the crust are due to compositional variations or fluids, both of these would sort of produce lower strength crust. So we think that part of the reason that we're seeing the Mackenzie Mountains where they are is because there's low velocity crust being deformed and forming this sort of arcuate shape, which matches the low velocities that we see. Now we can look into the mantle by looking at shear wave splits. The leftmost figure shows shear wave splits projected to 100 kilometers depth. And what the purple and green lines show two different methods of doing the shear wave splits, Silver and Chan and Menke and Levin. And what we see is basically a rotation from oriented with the tectonic fabric and the strike of the major faults, then a rotation, and then roughly absolute plate motion in the Northwest Territories in the Mackenzie Mountains. This plot here to the left is the shear wave splits are plotted on S-wave velocity at 100 kilometers depth to see if there's any variation due to the low velocity features we see here. To the right, we've done station averages. So assuming that there's only one layer of anisotropy, we've stacked the uncertainty surfaces, and what we see is the green splits, which align with the tectonic fabric, the purple splits, which show rotation, and then the Mackenzie Mountains splits and cratonic splits, which seem to match with absolute plate motion. Now, if the lithosphere is only 50 kilometers thick, the southwest splits must be due to a sinospheric strain. So here I show the figure that I showed earlier that suggests, at least on the Canoe Array in the southern part of our model, that we have a 60 kilometer or 50 kilometer thick lithosphere. To the left here, I just show 3 models that Audet et al. Have presented for the lithospheric architecture of the area. And regardless of which model we use, what we see is thin lithosphere to the west and thick lithosphere to the east. So what we think is whatever is happening is the shear wave splits have to be produced by the asthenosphere, because there's just not enough lithospheric mantle to produce the average 0.8 seconds of shear wave splitting time. So to figure out what's happening, we've used the global tomography of Wang et al. So they take density variations inferred from global tomography, and they've created a global geodynamic model. The red lines show the inferred fast axis from the Christoffel matrix, averaged between 400 and 100 kilometers depth, so the area that we'd expect to see anisotropy in. And what we see is basically, especially if you look at the purple splits, the rotation and the inferred asthenospheric flow direction shown by the red lines do not match at all. So we think that at least to the western part of our array, what's happening at a global scale is not affecting our shear wave splits. So another thing we can look at is the Finsel et al. Plate tractions model. And here I've shown an updated version from Lucy Flesch et al. And you can see that they've updated their model to go much further east. So the red arrows show inferred plate tractions, again, where they've tried to fit plate boundary motion, plate boundary forces, gravitational potential energy to measure GPS. And what we see is, again, the convergence of plate tractions under the Mackenzie Mountains. But what we don't see is an alignment of these red arrows with the shear wave splits. We do see an alignment of crustal anisotropy. So this is 0 to 30 kilometers receiver functions, where they looked at the transverse channel and they calculated the fast axis orientation. And what we see is roughly crustal anisotropy oriented along the tectonic fabric here. We can go from 30 to 60 kilometers depth, and we don't see it as much, but 0 to 30 kilometers depth, we definitely see it. And I'd note that the tectonic fabric, so here is another figure that shows the accreted terrains in the area, tends to be oriented in the northwest-southeast orientation, again in the direction of our shear wave splits, at least to the west. So perhaps the lithosphere here is thicker than 50 kilometers and the splits reflect 150 million years of transpression. The anomaly that we see in the body wave tomography, this is the P wave tomography, definitely suggests that lithospheric structures may be deeper than 50 kilometers, at least for certain local areas. Another possibility is the formation of a slab window. So we had a mid-ocean ridge subduct under here about 35 million years ago. As the mid-ocean ridge subducted, we had a lack of a slab subducting under this area, and this area has grown both to the south and to the north. Volcanics have increased to the north and the south, starting right here, about 35 million years ago, consistent with the subduction of the mid-ocean ridge. And so what we think might be happening is that we've had a stenospheric upwelling in this area here, whereas this area, the Yakutat Pacific slab and the Juan de Fuca slab have been sort of protected by subduction. So if I look at a transect, this is going from south across the Juan de Fuca plate to the area of the Mackenzie Mountains, at least the southwest part of our array, to the Yakutat Pacific plate, that there's been a slab window pair here, and there's upwelling a steinosphere. So that would potentially create a orientation of shear wave splits that are associated with upwelling a steinosphere, and then a rotation as we enter an area that's less affected by upwelling a steinosphere, and then finally a high shear wave splits that are associated with the craton and absolute plate motion. Now you may wonder why cratonic shear wave splits would correspond to absolute plate motion, because you'd think, oh, cratonic lithosphere is 200 kilometers thick at least, so there must be a distinct lithospheric component. Well, we don't really know for sure if it's absolute plate motion or lithospheric anisotropy, but I can say that shear wave splitting measurements taken off further east from this area have also inferred that absolute plate motion has been causing the general fast axis orientation. All right, so what could be happening here? Here I show the P wave velocity at 100 kilometers depth. Well, there's probably upwelling. This upwelling may be associated with the opening of the slab window. There's probably transpression and downwelling. So E was a narrow anomaly that seems to go to at least 200 kilometers depth, and it seems to have sheared off of velocity anomaly B down here. So we think that this was originally thick lithosphere here, as well as thick lithosphere here that's been sheared to the northwest. And then more recently, the Yakutat plate has created a strain knot, and that's caused deformation to move towards the northeast, and that has spread, and that forms the basis of the Mackenzie Mountains as the low velocity features run into higher velocities and stronger lithosphere to the east. So what we've learned so far is that the velocity structure is much more complex than fast to the east and slow to the west. The possibility is that cold cratonic lithosphere has been sheared by the faults. The deeper structure, so if you look back at the tomography, we found high velocity features at 400, 500, and 600 kilometers depth, remains of unknown cause. It matches no known plate reconstruction, so we don't think these are abandoned subducted slabs. I think that both the crust is being pushed by the Yakutat, but also plate tractions are causing as well, playing a role in the current uplift. And I think this is being focused by 3D variations in velocity, and we really need to create a 3D velocity model and do a deformation experiment with this 3D model. We don't know what's causing the huge low velocity in the crust right now. This could be fluid, could even be magma. And I don't know how to reconcile the 3D velocity structures with past deformation. So what we see is what's happening today, what's corresponding to the deformation happening today, but we also know there's been 3 series of uplifts in the past, and what's caused those. The Yakutat indenter has only been going under Alaska for the last 12 to 20 million years. So past deformation cannot be dependent on the Yakutat indenter. All right, thank you. Any questions?
Derek, thank you so much for the wonderful presentation. We learned a lot about your research during this 45 minutes of time. There are a few questions I could see in the chat box.
All right, yes, I see those. Does the Yakutat collision cause crustal thickening? If so, then how? I don't know about what's happening actually at the Yakutat collision. I presume it is causing crustal thickening because you have uplift of mountains in the areas, the Wrangell-St. Elias range. And as those isostatically relax, you will have thickened moho. In the Mackenzie Mountains, a large number of broadband seismometers were installed. What challenges were faced during installations and operating of instruments in a terrain like the Mackenzie Mountains? So I kind of glossed over it, but it was very tricky. So we would be dropped off by a plane in many cases, and we'd have 3 or 4 hours to put the seismometers in. And sometimes the plane would arrive and we weren't finished, but the plane would have to take us out anyways because they were on their own schedule. So we faced the challenges of getting equipment in efficiently in very remote circumstances. It snowed on us in August, so the weather was challenging at times, and the mosquitoes were absolutely terrible. But it was also very fun, and we got to see a very remote part of the world, probably the most remote part of North America. How I made such an impressive map. These were made using GMT. So, and I'd be glad to send the shell script I used to make those maps.
Okay.
Why is the moho elusive under the Mackenzie Mountains using receiver functions? Well, the reason is basically a lack of data coverage. So between the end of the 4-wheel drive road in the Yukon Territory and then the first lake that we were able to put a seismometer in the Northwest Territories, there is about 80 kilometers where we just couldn't find a place to fly into. So we didn't have a seismometer put there. So unfortunately, that also seems to be an area where there's significant crustal structure. What is the reason for such velocity variations across the Mackenzie Mountains? That's a good question. I don't really know right now. What we're thinking about doing is writing another proposal to go and put magnetotelluric instruments out and see if these are actually fluids, especially in the crust. I don't know what else could be causing the strong velocity variations. In the mantle, I think it's more lithospheric fragments and upwelling asthenosphere causing the velocity variations. Does the tectonics process under the Mackenzie Mountains have dependence in triggering seismicity during the Denali earthquake? So the Denali earthquake has caused the GPS instruments to have a transient signal. And so they have to remove the transient signal from the GPS before they can look at the long-term tectonic implications of the GPS signal. And that is done by colleague Jeff Freimuller and Connor Droth. I've just focused on the seismology. Did I get any hinge fault along with large CLVD components of focal mechanism? No, and I haven't looked at the focal mechanisms myself, so I'm not sure if those are actually large CLVDs or just poorly determined focal mechanisms, because they're using a very sparse array of seismometers. But that's a good question, and I don't really know. Why less seismometers are under the Northwest Territories? That was because of expense. So it was really expensive to charter a plane and fly it into a lake. And so we had to limit the number of seismometers that we put in up here. Even so, it was the largest proposal ever funded by the NSF Erscope program. And all that money went towards field work. Very little went towards data analysis. So we're doing the data analysis right now. Maybe the lithosphere has been ruptured orthogonally to the trench. It's certainly possible. I'll have to think about that. What are the array constraints that we need to consider for study in such terrain? Well, I guess we did not have self-contained three-component. There's a type of seismometers that they're basically a large cylinder that you stick in the ground and you don't have to dig a pit. And we didn't have those. So we had to dig a pit, put a concrete pad in, put the seismometer on the concrete pad, and then run the power supply in a separate container that we also buried due to temperature variations, because it gets to -40 to -50 degrees C in this area. So we were actually quite worried about having power in the winter. We did add air cell batteries to power this in the winter when there's very little solar energy light. That is also an array constraint that we had, is just keeping things powered. Also, we were only able to visit our sites once a year due to the cost. They were not telemetered in or anything like that. So we did not know whether our sites were recording or not until we actually got there a year after they were deployed. Why is split more on the Denali fault? So that's a good question. And we see splits increasing on the Denali fault and then increasing on one side of the Tintina fault. Clementa Stev has proposed that is due to the lithospheric shearing of the faults. So what we're measuring is increased lithospheric thickness and sheared lithosphere. It's not consistent though. In areas further north and south of our array, we don't see the increase in shear wave splitting. So I don't really know what to make of it. The negative amplitudes are adjacent to the positive amplitudes for the MOHO. Could it be an artifact? Pascal Audet did the lithospheric receiver functions. He's very good at what he does, so I trust that he did it properly. What I showed you actually wasn't the PDS conversion, but it was a cross correlation of the PDS conversion. So it actually amplified the PDS conversion off the base of the lithosphere. So what I showed you was actually sort of a derived figure. But that said, do I really trust receiver function results? You know, I'd love to see lithospheric thicknesses done in the Mackenzie Mountains and the transportable arrays. And I don't know if any of my colleagues are working on that. We're working on that, but right now we're focused on the ambient noise imaging. Yeah, right now.
So I think, okay, please go ahead.
I have one more question. Why we use linear arrays for recording? That was just because we were unable to put in a two-dimensional array just due to the cost. So it was basically all we could do to get 40 seismometers in a line. At least the line transected the Mackenzie Mountains, so it allowed us to do a cross section through the Mackenzie Mountains. And then with the transportable array, which was over to the west in Alaska and Western Yukon Territory, we were able to get crossing rays for ambient noise, which was useful.
So I think students have asked a lot of good questions. That's quite nice.
Yeah, it was amazing questions.
Yeah. Because they are just master's students having entered into this geophysics program. So, so for them on the level, those were pretty good questions, I suppose. So thank you, Derek. It was a wonderful presentation where we learned a lot about your research in Mackenzie Mountain, where you performed ambient noise tomography, body wave tomography, receiver functions, and shear wave splitting, etc. And we also could hear wonderful interpretations to the results, whatever you have produced. May I ask my HOD if he has anything to say?
Okay, go. It is a fine. Many thanks to Derek. At the early wee hours of the day, you are giving a lecture to our student. It was very nice and interesting. Many thanks to you.
Thank you.
And also I think I will consult with Derek. So we are soon going to organize a GYAN course, which is actually pending from a long time because of the pandemic restrictions.
Okay,
so
very good.
We will look into that. So I'm sure that the students have learned a lot during this talk about the research on receiver functions and shear wave splitting and body wave tomography. So with this, and the entire department of Applied Geophysics is very much thankful to you that you could actually deliver this presentation in such an early morning. And we would also love to hear more about your research in the near future if you will provide the opportunity for us to do so. So we will be in touch, and thank you so much. That is all. Thanks.
All right. Well, thanks a lot. And I guess I'll say goodbye. But thanks. It was an honor.
Yeah. Thank you.
Okay.
For us to have you here on this platform. Thank you.
All right. See you all.
Okay. Bye.